Good morning. Thank you for making time to come to the talk, and thank you to the IEEE ComSoc and to the organizing committee for inviting me here to talk about our work. I'm going to shift gears a little bit and talk about some of the underlying technologies and some of the problems that we'll be facing today in the Data Center Interconnect. And I'm going to talk about a concept called quiet light. I'll get to that about halfway through the talk. So I'd just like to acknowledge our collaborators. It's a long list, I won't go through it, but you'll see Yale, Microsoft, NIST, Honeywell, Stanford, and others up here. There's a lot of people involved in this work. And also our funding agencies, DARPA, the DoD, MTO, ARPA-e. I'll talk about a lot of work from ARPA-e, the OPEN-2018 program, and then again we have companies that sponsor our work too. And then, of course, we want to give acknowledgments to the people that work. This is the current group in my lab, and you can see that we have work in energy-efficient WDM Coherent. We make our own photonic circuits. I'll talk a little bit about this technology. We're integrating atomic clocks on chips. We also do work in quantum and integrated gyros and other technologies. So let's back up a second from the technologies and talk about what are some of the issues that we face today. We'll start at the top and start working our way down towards the technology stack. So hyperscale data centers. This is from the Cisco report, and you can see that today we're at about 12 zettabytes per year. And it's expected that we're going to see upwards of 20 or more zettabytes per year in the data centers themselves, and that's going to be supporting traffic that's being sent, which is quite larger. One of the issues, though, is these hyperscale data centers are actually going to be starting to consume more percentage of the internet. In other words, today, we're about 44%, but by 2021, we'll probably see 53% of the data centers will be hyperscale data centers. So the question is, what does this mean? This is a traditional DCI. It's a fat tree. It starts with our servers, top of the rack switches on top of the servers, and then you build the rest of the network up with spline switches and other layers of switching. And what supports this level of Ethernet switching inside the data center is something called a switch ASIC. These are extremely high-powered Ethernet packet switches inside silicon. Today, state-of-the-art switch ASICs can actually route 12 terabits per second through the input to the output, and they sit in a chassis that I'll show you. I mean, that's quite amazing. It wasn't too long ago that we were dealing with 2 terabits per second in a single switch ASIC. What we find happening is that the lower bandwidth ASICs sit at the top of the rack switches, and then as we aggregate the data, the capacity of these switch ASICs has to increase as we go up the stack. But over time, the data center capacity increases, and these high bandwidth switches start making their way down the stack, and you have to create new switch capacities that can work higher up the stack. And that's unless you actually flatten out the technology, but that's the subject for another talk, flatten out the architecture. The point is that it's not going to stop here, and it's going beyond where people thought it would go. This is what we're dealing with today. This is a barefoot chassis. And what you see on the left-hand side is their Tofino 2 12.8 terabit Ethernet packet switch. If you look over here, this is the box itself, and underneath this cooling system here is actually the switch. So you need this whole part of the chassis here just to cool that 12 terabits per second. What's in the front is all of the optical I/O needed to perform the uplink functions to send the data out and bring it back from the higher parts of the network. The servers are connected at the back end. But notice that the optics takes up way more size than the electronics itself. These are pluggable modules, plug in, and the fibers connect to them. And what you're looking at here for the Tofino is 32 pluggables transmitting 400 gigabits per second, each pluggable. That's what you need to support the I/O for the 12 terabit per second switch. This is amazing compared to what we thought we could do, but as you're going to see, it's going to start pushing the very boundaries of engineering and what can be done. Let's look a little bit under the hood of a silicon switch. So here's a 12.8 terabit switch. Typically what happens is the outside of the switch can support so many I/O connections. For example, 256 pins. That tends to be the limit, or a limit. And how much bandwidth can you push over those 256 pins? Well, in this case, they're starting to push 50 gigabits per second times a PAM4 data format coming out of the electronic transceivers on this chip. That's a lot of data coming out of a chip. And that data today is achieved by increasing the density of the transistors by 1.8x. The problem is they can only do so with a 20% power reduction. And I think you can see there's a problem there, right? You increase the density by 2x, and you only save power 20%. Problem is you can only burn so much power in one of these chips and offload them. So what we start to see is a Moore's law for network, where we need to continue to double the data of the interconnect, the capacity of the interconnect itself, but the actual switches themselves are burning so hot with so much data that they can't communicate in and out anymore. And we run into a problem where we can scale. Believe it or not, today, people are talking about these chips scaling out to 102.4 terabits per second in a switch chip. What is this equivalent to? If we go back to the 2004-2013 period, this is what the Cisco CRS looked like. It was 72 racks of I/O, buffers, and other functions, including the fiber connect, as well as 8 racks of switch fabrics. These were 40 racks and 92 terabits per second, possibly 322 terabits per second, required a whole room. What we're talking about right now is taking all of the electronic switching functions and all of the buffers from this Cisco system and putting on a single chip. That's what we're talking about. But what's not going on the single chip is any of the optics. So all of the optical I/O and all of the lasers and detectors and optical functions and fiber connects that were in these 72 racks, we don't know how to get them to connect with this switch chip if it goes to 102.4 terabits per second. That is a problem. These are busy charts. I won't talk about them in detail. And everything I'm showing, by the way, is publicly available. And I've provided the links down below. The problem is that the I/O on the package is limited in bandwidth. Let's just pay attention to this curve right here. So here's the total power in a package. And we're looking at watts, so we're getting out to 100 watts up to a kilowatt out of a single switch package. The I/O, the way driving the optical signals from that switch itself over time has climbed up. But you want to hit, from a designer point of view and from a practical perspective, you don't want to have the optical I/O exceed that of the electrical I/O. You want to keep the power envelope flat. That's what we say. And at some point in 2020, that's probably not going to work anymore. In other words, the I/O for the optics is going to start outstripping the power of the electronic switch itself. So this is a problem right here. Another way to look at it is shown here. Today, our switch communicates out to optical I/O on a board. In other words, you saw that chassis, and we had our switch chip talking to these optical pluggables here. Today, we talk 200G modules using 4 fibers times 50 gigabaud. We're about to move to 400G modules, which will talk 4 fibers at 50G PAM4. The question is, can you keep going? Can you have 800G 4 fibers with 100G PAM4 and keep going in this model here? And the answer probably is no. Because look at this picture right here. This is the number of modules. Remember our box with all the modules in the front? If we keep going this way, we're going to need 512 modules sitting on the front. Highly unlikely. We're going to need 4,096 fibers coming out the front of this chassis box, like a 1U high, 2U high pizza box. Probably unlikely. So this blob right here, this gray zone, with 25T, 51T, and 102T switches, and people are starting to think about higher capacity. There's a zone here where powering and engineering limits probably hit us. And the question is, what are we going to do? The engineerable solutions that people look at today, and there's companies, there's funding agencies, there's universities looking at this problem, can be bundled up into moving the pluggables on board, and there's the COBO initiative with Microsoft and Facebook leading it and other companies to move those pluggables onto the board. There's moving the optics into a package, so co-packaging the optics with the electronic switch chip itself. And then there's actually putting the optics on the silicon itself. Today, I'm going to talk about this middle one here. Okay? This one here, on board, is probably not going to work as we scale to 102 for many reasons. So the solutions are probably going to sit in these two spaces here. What this requires us to do is we look at in-package, on-board, and off-board. These are the distances that we can throw the signals, right? So here's inside the package, here's on the board, and here's to the modules. What we have to do, and the problem that we have to face, is we have to communicate with energy per bit that is equivalent to how much energy it takes to move the bits on the chip itself. And if you think about this, it's a really hard problem. On the chips themselves, people move to do about 0.1 to 2 picojoules per bit of energy across that 12 terabit or the 25 terabit switch. But once you move it on board or to the optics, you're at 10 to 20 picojoules per bit or up to 100 picojoules per bit. And that's where the system burns too much energy. And you pay all these taxes. So what people want to do, the solutions that they're seeking, is to make the energy to talk across the chip or even across a fiber link the same. In other words, for those of you who think about just moving data from a networking perspective, in other words, throughput and latency, which we heard in the talk before. Throughput and latency is one metric. People try to flatten the network out. They try to get equal latency, for example, from a memory cache close by or a cache that's far away. Now we have to think about the problem with energy per bit. It only costs me, say, 2 picojoules per bit to go across the chip or to another box. And that's the challenge that we face today, is to try to make energy consumption of transmission flat and independent of the distance that we throw the data. Well, how do you do this? What we advocate in our group that I'll talk about today and is being advocated by others is to bring something called coherent WDM inside the data center. This is not as easy done as it sounds, and I'll talk a little bit about it. People do not use coherent WDM inside the data center today, and I'll talk about why. If you can use a coherent solution, what I'd like to do is just show you here the power of the switch ASIC as we go to 102.4, say heading out to about 600 watts in a switch ASIC. The I/O using old solutions or today's solutions, they just take off. So we don't have this matching anymore. We run out of solutions using today's solutions. And then if we can make coherent optical WDM, we can track the power for the I/O interconnect to track the envelope of the switch ASIC package itself. This is the kind of behavior that we want when we engineer these boxes with switches and the fibers coming out of them to make the fabric that what we saw in the earlier talk, the keynote before, use this fabric. This is the way to scale. So let's talk a little bit about what is digital coherent WDM, for those of you not familiar with it. As a matter of fact, a lot of this technology is very similar to what we use inside our cell phones, right? This is a coherent transceiver. It uses QAM, a very sophisticated QAM formats. The question is, can you do this in optics? And the answer is yes. But it takes a lot of work and power and sophistication to do it in optics. You're dealing with carriers whose frequency is 200 terahertz, 400 terahertz, as opposed to working with gigahertz carriers in the RF and microwave domain. We have transmitters that produce colors of light, lambda 1 to lambda n, different colors. They are being driven by digital signal processors that take the data and do things to the data in order to create something we call a data constellation. The data that we're pumping through the transmitters on these different colors of light are mapped out to symbols, like we do with RF and other techniques. These are symbols. Each symbol carries a binary set of data. Today, people can transmit out to 1024 optical. It's not used very often. If we look in the network, we're going to find 16 QAM, and soon we'll probably find 64 QAM. But in research, we do move out beyond that. At the receiver end, what we do is we take these data streams on different colors, we bundle them up on the fiber, we transmit them and amplify them, and then we peel them apart at the receiving end, and we analyze each color separately using a receiver and a DSP. The DSPs were developed to overcome the limits of unperfect lasers and analog systems that people used to use. High-performance DSPs made something called phase locking not necessary anymore. When you dealt with old school FM receivers, right? I don't know how many people remember the knobs that you turn, and you had to lock into the FM channel, and it had something called a PLL, so it had to grab the transmitting station, and indeed our satellite receivers have to do this. They have to phase lock to the incoming signal, okay? Well, in optics, this is hard to do, and it consumes a lot of power, so these DSPs made it so you didn't need to use phase locking anymore for the data, and I'll talk about that in a second. So you're running your local oscillator, your laser, over here free running. The problem is there was a trade-off. These DSPs consume a lot of power. Today, a 400 gigabit per second coherent WDM DSP consumes 10 watts for 400 gigabits per second. Now think about that for a second. If we try to take 400 gigabits per second and scale it to 102 terabits per second, at 10 watts per 400 G, I think you can imagine it doesn't work very well. Here's, if we take the hood off a coherent WDM system, this is what it looks like. We take data coming in, we error correct with 4 error correction, we do symbol mapping to create the symbols. We use digital to analog converters to make a joystick. It's like a Etch-a-Sketch or a joystick for a game. And that joystick drives a modulator that makes the laser itself move around this constellation. So this DSP is literally driving the laser around the constellation. And at the other end, we have another laser that's sitting there. It's being mixed with the received data. We're going to convert it back and do the inverse function with DSPs again. The functions that we have to do are we have to take the 2 frequencies of light, which are not the same, and we have to zero out the difference in frequency digitally. And then the 2 lasers, phase, the actual phase is different. And we have to cancel out that phase or track it. And that's also done by the DSP. And that's done in the next stage. And then what we do is recover the data. The problem with all of this right here, I've shown a little burner stove down here, is that it's hot. And if you want to take this system and move it into the data center to solve the problems that we were talking about before, how are you going to do that? And that's the question. So what I'd like to talk about now is one approach, because there are several, and it's something called quiet light. And the question is, what is quiet light? Quiet light is like an optical tuning fork. If you have a tuning fork and you hit it, it can emit really good tuning forks, a perfect tone. Continuous frequency, doesn't change very much, lasts a long time. Quiet light is an optical source that's spectrally pure. It can emit a continuous frequency of light. Close to 0 fluctuations in the frequency of light. Ideally, you could have 2 different optical sources that behave as if they were one source. Their frequency itself doesn't drift very much over time, and I'll talk about this in a minute. And also the amplitude is stable. So this is quiet light. Lasers that we use today in data centers and for optical communications are not quiet. They don't have these properties. People try to make them as good as they can, but they're only so good, and in the end, you have to hang these DSPs off them because they're not quiet. What is the quiet light of big science? There's two areas where quiet light grew up in big science. One of them was atomic clocks, and the other is LIGO, the laser gravitational wave detector. This is a strontium atomic clock at NIST. Strontium is an atom. It has some nice properties I'll talk about just in a second. You can see that there's all these fancy lasers needed, vacuum systems. Basically, they take a room full of equipment. Over here is the gravitational wave detection system. This is just the laser. Only the laser part of LIGO sits in a room out on this huge table with all this fancy equipment. I think we can also agree that these systems are not going to go into the modules on the blades for a data center interconnect. But is there something about these systems that can be moved on chip and used to try to address the issues that I talked about before? Over the years, Nobel Prizes were handed out. A lot of science was done by a lot of people and engineering to make quiet light in these systems. Is there something about these systems and the quiet light that we can take and move on chip to do data center interconnect communications differently? That's the question. Here's a cartoon of an atomic clock. I just want to illustrate that as fancy as they are and as much work has been put into them, at the high level, there's something simple about the way that they operate. We have an atom or a group of atoms that are being contained in a certain way. And there's a laser that has to sit there on the side, and it's like the signal that came from the satellite or the FM system. At some point, it's going to have to lock to the atom. In other words, at some point, we're going to actually turn the system on, the laser is going to lock to the atom, and the laser is now going to be referenced to an atom. Really stable nuclear forces. So the laser is going to take on the quality of the atom. But the system is being run in two different modes. One is in open loop. The laser's just kind of waiting there, and the atom's over here, and they're doing stuff to the atom. They're cooling them down. They're getting them in the right place for the laser to talk to it, which requires some work. In that whole time, the laser over here has to be stationary enough so that it's sitting there within the atom resonance, just sitting there, so that when they then turn the system on, the lock, the laser readout, it's within range and it locks up. In other words, that light source has to be very quiet, extremely quiet. That's what took the room full of equipment. Now, once you take that quiet laser and lock it to the atom, it's really quiet. In other words, it takes on the properties of the atom. To give you an idea of how quiet this system is, today, the universe is about 13.7 billion years old. And when you put it down in seconds, it's that number right there. The best atomic clock, strontium, today, is accurate within 1 × 10⁻18th fraction. And what boggles the mind is that if you were to take this atomic clock and you had turned it on at the start of the universe, till today, it would have only lost 1 second of time. So I hope through this statement, you now get an appreciation for what quiet light might be. Okay? Once you lock it to an atom, it's light that's quiet enough that could be light that's been around for almost the age of the universe. Okay. So let's bring ourselves a little bit back into the engineering mode and the data center. Today, atomic clocks are actually used in the network. Many here at this conference might know that because this is part of your field, but some may not, that back in the early 2010s, Google launched TrueTime and Spanner for database synchronization. TrueTime and Spanner have atomic clocks and GPS located at key nodes so that the time at each node is absolute within the precision of an atomic clock. This way, when you timestamp transactions, like bank transactions or other transactions that require absolute precision, their stamps are done with local time that's accurate to within that of the atomic clock. Now, this is a very important tool for building distributed databases today. There's many more applications. And I also would like to give disclaimer, or just, I should say full disclosure, that while this one is based on atomic clocks and GPS, there are other approaches like Azure, Cosmos DB, and UByte DB that don't use atomic clocks. There's different ways of building these very precise database synchronization systems. But the point is that people already are thinking about atom precision stabilization and timekeeping in a network. It's not far-fetched, right? Today, in our group, we make quiet light sources and we've moved them onto chip. In the center here is a cartoon of a laser that we make. It's called a stimulated Brillouin laser, and it's very quiet. It has properties about it that calm the light down and make it really, really quiet. In our group, we have projects to put an atomic clock on a chip. You see here the atoms being held and the quiet light source talking to the atoms. We make optical gyroscopes using quiet light right there. RF microwave synthesizers, and today I'll talk about a project that we have for transceivers, 4 terabyte data center interconnects based on a quiet light source like that we would use in an atomic clock. So this is the question, right? Can we take quiet light, put it on chip? If we can put quiet light on chip, can it be a building block to now make circuits and other technologies that can be used, in particular for this talk, for data centers in terms of transceivers? Just some interesting points on here to note. Here's our quiet light source. I'll talk a little bit about this source here. It takes one color of light and makes many colors of light. So actually, I'll show you in a minute, this makes a whole band of quiet light. These are the modulators and demodulators over here for the data themselves. So how can quiet light be applied to scaling hyper data center interconnects? We have a project with ARPA-E called FRESCO. It stands for Frequency Stabilized Coherent Optical in the Data Center Interconnect. It's a highly integrated, co-located transceiver. Very low energy, 1.6 terabits per second per wavelength, per polarization. Ultra high frequency stability, no DSP. Remember the burning flame with the DSPs? They're going to be taken away. So how can you make this without a DSP? It's a good question. People put DSPs in there for a reason, right? How can you do it without the DSP? In order to put this in the data center, the DSP has to go away. We also don't use other high bandwidth components like OPOLs, EPOLs, Costas loops, all these technologies that people make for tracking signals. They don't scale well when you go to optics and when you go up to very high data rates. So here is our quiet light WDM source. This is WDM for wavelength division multiplexing. Here's our Brillouin scattering laser. Here's a cavity that makes the laser quiet. And this is a comb source that makes many colors of light. So one quiet light makes many colors of quiet light in this transceiver. And many years ago, in the early 90s, I was in meetings with Vincent Chan, and the networking communities and the optics communities were being brought together for the first time to make optical networks. And people were talking about moving something called solitons over fiber. Solitons are very short pulses of light. And Vincent and I were in these meetings, and everybody was talking about how to make networks out of solitons. And at this meeting, Vincent asked me if solitons are still being used, and I said no, not to move data around the fibers, but they are being made inside a little component on the chip. So for Vincent Chan, I made a little diagram here which says solitons inside. So inside this little ring right here, there actually are extremely short pulses running around. We make quiet light talk to them, and they generate a whole band of quiet light. It's called a soliton nonlinear comb generator. What does this have to do with coherent networks? How is this going to help solve the problem? Well, here's an analogy. It's a loose analogy. Let's say that we were out in the bay over by, say, the Marriott, right? There's the little bay right there. And let's say that we put 2 aircraft carriers in there. Not that we would want to, but let's say we did, right? I think we can all agree that they're going to be pretty stationary, right? They're big masses. They're just going to be hanging out, right? The perturbations of the water and the wind probably are not going to do a whole lot to them. And now let's look at this little diagram right here. What's going on? Oh, there's 2 sailboats there. By the way, their sails are lowered. And they're tethered to the aircraft carriers. So they're not free-floating, right? The aircraft carriers are very stable, and the sailboats are now being stabilized by the aircraft carriers, right? Let's look. We see something else going on there. There's 2 people. One of them is trying to take a thread on one boat and put it through the needle being held on the other boat, which we can all agree would be a very difficult task. But we could probably agree that because the 2 sailboats are tethered to the aircraft carriers, the 2 people are probably having an easier time than if the aircraft carriers were not there. They would probably be running around the deck, trying unsuccessfully to thread the needle, expending a lot of energy, having to go back, eat some food, some drink, go back, try it again. They're expending a lot of energy. But now we stabilize the boats to the aircraft carrier, and they're probably expending a lot less energy to put the thread through the needle. The masses of the aircraft carrier, which are physics, are allowing less energy to be expended. Sound familiar? Here's a laser, a tunable laser whose frequency can be tuned. Here's something called a microcavity reference. It's like the aircraft carrier. It's an optical aircraft carrier you can think of. The tunable laser is being anchored to the reference cavity so that the light is very quiet and stable. So we can now take the signal in the local oscillator and we can thread them through a microwave filter to recover the signal with very low energy, without having to track them with DSPs or do very high bandwidth work to try to align them, because they're very stable. Here's an example. This will be presented at OFC in March. OFC is the Optical Fiber Communications Conference. IEEE ComSoc is jointly sponsors that. And my student Grant and others did this work. So this will be presented. It just shows a cartoon of taking this tunable laser, quieting it down with this brilliant lasers that I talked about, and then anchoring it to a very small microcavity. And that creates this very stable source that is then repeated at the transmitter and the receiver. There's 2 technologies that we use to do this. I'm not going to go into them in any detail, but if you're interested, one of them is in the proceedings of the IEEE special issue of Silicon Photonics from December 2018, and that's the waveguides. The wires on the chip themselves that move the light around have to be very low loss. You cannot lose many photons. And so the lowest loss waveguides on a chip today are being made and used for these technologies, and we talk about that more in this article. And this is an optical waveguide right there. Like a circuit trace for electronics, but this is to move the light around. And also, if you're interested in reading more about our quiet laser, it's made with the very low loss waveguides. And in Nature Photonics in January 2019, there's a picture of our device there, illustration. You can go and read more about that too. And this is how we use quiet light to build a link. We have a transmitter that uses its own quiet laser to make a constellation. At the receiving end, we have another quiet laser. These lasers are so stable and quiet with each other that we only need 100 kilohertz phase lock loops to align them. And those 100 kilohertz loops can be made on bi-CMOS circuits with about a milliwatt of power. So for this particular link here, you need about 5 milliwatts of CMOS to align two lasers to transmit terabits per second of data. And that's a lot better than 10 watts for a 400 gig channel. And I'll just show this quickly. This will be presented at OFC in San Diego. It actually does show the system running. And I just wanted to show you really quickly that here's a full throttle DSP recovering the constellation at the receiver. And here's our technique with no DSP recovering the constellation at the receiver. So this technology is now being proved out. And I'd like to stop there. And thank you very much for your time.
Again, thanks to our distinguished keynote speaker for such a great technical talk. So we have a couple of questions from the audience. So the first question is about, so they ask, as the source becomes perfectly quiet, they would expect the loudness in the system becomes dominated by other elements. So how close are we to the limit, and is that important or not?
That's an extremely good question. I mean, I don't go into the details here, but we measure the quietness of the source by measuring the noise as a function of frequency. We look at very high frequencies. We look at very low frequencies. These frequencies are used in LIGO and atomic clocks. They go down to 100 hertz, 10 hertz, 1 hertz, 0.01 hertz. You have to pay attention to all of these. And environmental acoustics, they are embedded down there. So the answer is yes, these are important. The answer is that we get rid of all the frequencies with the quietness, and what's left over, these external disturbances, are such low frequency that these circuits to quiet them down the best are now very low bandwidth, low energy circuits for finishing the quieting up.
So the second question is, with the deployment of edge computing, so what's the future direction of optical networks?
The question about future of optical networks with edge computing, I mean, it's going to depend on the hierarchy. Certainly, optics is going to need to scale well to the cost of the edge nodes. So probably we're going to be looking at a hierarchy of solutions with the more expensive ones in the higher aggregate nodes, and then with the edge nodes, you probably have to go to lower cost optics, just like you would in a passive optical network or some other kind of network like that.
Another question. So the audience actually would be very interested in knowing what unsolved research problems in the quiet light WDM you want to highlight to share with the GLOBECOM attendees.
Sure. I mean, quiet light is both new and old. I mean, as you can see, quiet light has been the mainstay of large-scale physics, right? But we're entering a time when quiet light is moving on chip, and that's new. So it's a new field. And getting all of the noise sources and the environmental conditions not impacting the quietness, getting them onto chips that can be made on wafer scale, so you can have a foundry make chips now, and getting those chips in a way that they can work with standard electronics is the next step. So those are really the important problems today, and there's a lot of materials underneath and good science to do still.
Great. Thank you again, Professor Blumenthal, for a great talk.
Thank you.